In this video, we'll go through a simple example of connectionist processing done on the simplest neural network, the perceptron. You can think of a simple one-layer perceptron as analogous to a neuron. Think of the body as the output unit. The dendrites would be the connections from the input units. Also, you can see the single-layer perceptron as either the simplest neural network or as the building block out of which neural networks are built. Single-layer perceptrons, for instance, a single output unit that received input from two previous units, can compute basic binary Boolean functions. But what is a Boolean function? Boolean functions are named after the mathematician and logician George Boole, who is famous for having systematized them. So a Boolean function is a kind of function, but I guess I didn't need to tell you that. But what kind of function, you ask? If you remember, a function is a mapping between two sets, one called the domain and the other called the range, such that to every member of the domain there corresponds at most one member of the range. The functions in this illustration range over numbers, but we could have functions over any kind of object. Boolean functions in particular deal with truth values. Let us assume that there are only two truth values, true and false. Then Boolean functions map one or more truth values in its domain to one truth value in its range. If the domain is composed of single truth values, then we have a unary Boolean function. A unary Boolean function then will map true in the domain to either true or false in the range, depending on the case, and the same goes for the truth value false. An example of a unary Boolean function is negation, which can be expressed in English as not P or it's not the case that P, where P can be any sentence such as snow is white or it's raining. Negation in particular maps the true to the false and the false to the true, so it simply inverts the truth value of the sentence it is applied to. For instance, suppose that P is it's raining. Then if it's true that it is raining, then the sentence it's raining will be true. Correspondingly, in this case, the sentence it's not raining will be false. So negation takes true sentence and outputs false sentences. Conversely, if it's not raining, then the sentence it's raining is false. And in consequence, the sentence it's not raining is true. So here negation maps falsity onto truth. To turn this into a numerical example, we can represent true by 1 and false by 0. So what negation does is simply turn 1s to 0s and 0s to 1s. One convenient way of expressing Boolean functions is by giving what is called a truth table. Again, suppose that P is any sentence and that the tilde symbol, that wavy thingy you have on the screen, symbolizes negation. Then tilde followed by P means not P. What this table tells us is that when P is true, then not P is false. And when P is false, then not P is true. And indeed, that's all there is to Boolean negation. When our function maps pairs of truth values to a truth value instead of single values to single values, we have a binary Boolean function. Here our domain consists of pairs of sentences, P and Q. So although in a unary table we only have two cases, namely one in which P is true and another one in which P is false, here we have four cases to consider. One in which both sentences are true, one in which the first sentence is true and the second is false, one in which the first is false and the second is true, and one in which both are false. From this we can see that there are 16 possible binary Boolean functions, that is, 2 to the power of 4 total ways of mapping each of those rows to truth values. Here we have a common example of a binary Boolean function represented by the ampersand. It is officially called conjunction, but we can call it AND because it does behave like the English word and. If you see P ampersand Q, it's true only when both sentences are true and false in every other case. Likewise, if I say I went to the movies and had dinner, well, this is only going to be true if it is true that I went to the movies and also true that I had dinner. If one or both of those things is false, then the whole sentence is false. Now, here's the trick. By representing true by 1 and false by 0, we can use single unit networks to encode Boolean functions like not and and. Notice that since the output is either a true or a false, all the elements in the network must be set up so that the output is either 1 or 0. To do this, we can use the binary threshold activation function. If you remember, the activation function can only spit out either 1 or 0, the threshold function, I mean. So it yields 1 when the input is equal or larger than a predetermined threshold, and it yields 0 when the input is smaller than the threshold. Okay, suppose that our output unit is C, which is fed by two units, A and B. The activation values of node A will correspond to the truth values of the first sentence, and the values of node B will be the values of the second sentence. The activation value of C will correspond to the truth value of the conjunction of A and B. Now the problem is, which threshold should we assign to C, and which weight should we assign to the connections to C, such that C yields a value 1 when A and B are both 1 and 0 in every other case. So let us begin with the first case, in which both sentences have the value of 1, and thus the value of A and B is also 1. We know that, as per the description of the case, the values of both A and B are 1. So let us set the weights for both connections at 1, and the threshold at 1.5, let's say. So according to our input function, the net input to C is the sum of the activation value of A times the weight of the AC connection, and the activation value of B times the weight of the BC connection, which is 1 times 1, added to 1 times 1, so the total input is 2. But our activation function outputs a 1 when the input is larger than 1.5, which is the threshold, as is the case here, so the activation value for C is 1. You can see that C is glowing with activation. That means that A and B is true, as required by the truth table. Let's now use the same weights and thresholds. Let's test it against the second case, which is the second row, in which A is 1 and B is 0, and therefore A and B is 0. The only thing that changes in this case is that the activation of B is 0 instead of 1, as in the previous case. So we'll follow our input rule, which in this case yields 1. And since the input is smaller than the threshold, the activation level of the unit is 0. But this is just as our truth table requires. I'll let you check that our threshold and weight assignments also work for the two remaining cases. So we know that the network can represent AND, but that is only half of what is interesting about neural networks. What is interesting is that it can learn to encode the function without any need for the weights to be manually entered. Neural networks are often used to model how information processing capacities are learned. In fact, there are two types of learning situation for a neural network. You have supervised learning, which requires feedback, and unsupervised learning, which requires no feedback. The simplest of the algorithms for unsupervised learning is what is called the family of Hebbian learning that use HEBB'S rule, and is based on this dictum by the neurophysiologist Donald Hebb that says that neurons that fire together wire together. And what he says in his book Organization of Behavior is that when an axon of a cell A is near enough to excite call B, or repeatedly or persistently takes part in firing it, some growth or metabolic change takes place in both cells, such as that A's efficiency as one of the cells firing B is increased. So what he means is that the connection between two neurons might be strengthened if the neurons fire at the same time, right? Now, in a simple form, the rule says that the increase in the weight of the connection between two neurons is directly proportional to the product of their activations. There are also supervised rules, and the most famous for perceptrons is the so-called perceptron rule, sometimes known as delta rule, and again was proposed by Frank Rosenblatt in 1958. And again, it is supervised because it depends on feedback, right, about what the intended output was. and it relies on the discrepancy between the actual output and the intended output to correct and to improve the weights. And so it contains a delta, which is an error measure, and is calculated by subtracting the actual output from the intended output. And well, the delta rule or perceptron rule gives us an algorithm for changing a threshold and weights as a function of delta and E, which is a learning rate constant, which tells you how fast your learning is going to go. And one of the things that Rosenblatt showed is that there was this formal guarantee that the perceptron convergence rule, right, will converge on a solution in every case where a solution is possible. That is, it will generate a set of weights and a threshold that will compute every Boolean function that can be computed by a perceptron, right, by our single layer network. But which functions are those? Well, before we deal with that, I'll leave you this as homework. This function is what is called inclusive disjunction or inclusive OR. It yields true whenever at least one of the component sentences is true, and it only gives false in the case when both are false. It is called inclusive OR because it is true whenever one of the sentences is true, but also when both are true. The word OR in English is sometimes interpreted like this. For instance, if I tell you you can satisfy this requirement by passing philosophy 1000 or history 2000, that means that passing one of those classes guarantees that you will satisfy the requirements, or also by passing both. That also works. Now, the V symbol in our table stands for inclusive disjunction. So your homework is to assign weights and a threshold to our perceptron in such a way that it encodes this function. Of course, disjunction sometimes works exclusively, as when the cafeteria lady tells you that you can have the pudding or the yellow for dessert, but that means that it's one of them, but not both, right? This function is also called XOR, and it yields true whenever one of the sentences is true and the other is false, and is false in the other two cases. Well, it turns out that our humble single-layer perceptron cannot represent XOR. Let's see why. Suppose that we represent a binary Boolean function like AND in a graph like this. So we have the values for A in the vertical axis and the values for B on the horizontal one. Note that each of the variables can only take 1 or 0 as values. Finally, in order to represent the values for A and B, right, that is our C, let us say that the white dots represent 0 and the black dots represent 1. So you can see that A and B only gets 1 when both A and B get 1s. That is, A ampersand B only gets 1 when both sentences A and B are 1, and gets 0 otherwise. Right? When you have at least 1 0, it goes to 0. Okay, do you think that you could trace a straight line that would separate the black dots from the white dots? Sure, here it is. Now let's look at inclusive OR. We get 0 only when both A and B are 0 and 1 otherwise. Again, it is easy to trace a straight line that would separate the black dots from the white dots. But things are different when it comes to XOR. There is no single straight line that will separate the white dots from the black ones. In short, Boolean functions like AND and inclusive OR are what is called linearly separable, whereas XOR isn't. Well, it turns out that the class of binary Boolean functions that are linearly separable are precisely those that can be encoded by single-layer perceptrons, and also the class of functions that is learnable by the perceptron rule. And well, that's basically what perceptrons, single-layer perceptrons do. They basically are linear classifiers. In this case, they do it by tracing a single line because we have 2 dimensions. But if you have more inputs, well, you would have a sort of a plane or a hyperplane. But those are the limits. Now, it turns out that if we add another layer, we can indeed represent the XOR function. So, for instance, this set of weights and thresholds. For instance, we are have two hidden units, x1 and x2. And x1 we have given a threshold of 2, and x2 a threshold of 1. And both A and B feed to x1 with a connection weight of 1, and both A and B also feed x2 with a connection weight of 0.5. Now the other feature is that x1 has a negative connection, an inhibitory connection to the output unit, which is C, which encodes A XOR B, whereas x2 has a positive connection of 1. So let's see in our first, in the first case, let's test it. In the first case, when A and B are true, A XOR B should be false, right? Should be 0. And indeed, in this case, we have that the input to, for instance, if we see, let's see what happens to the hidden layers. In case of x1, its net input would be 2, and that is that is at least as large as the threshold. So its activation is going to be 1. And in the case of x2, we also have an activation of 1. But that means that when we calculate then the input for C is going to be 0, right? And that's not sufficient for it to be activated. Suppose that the threshold for C is going to be 1. So this is exactly what is to be expected, right? And I'll leave you to check the other values. But if you notice, what is going here in the hidden layers is kind of transparent, in the sense that, for instance, you can see that A XOR B is equivalent to A or B, and not A and B. Think about it. Right? And what x2 is coding for is basically coding for OR, right? And what x1 is doing is coding for not A and B. And so this is basically what's going on in the hidden nodes. Okay, so we know that we can add another node to make our perceptron work, and another layer, I mean. However, in the 50s and 60s, there was no rule that would guarantee that would allow multiple layer perceptrons to succeed at learning. Nothing that guarantees that they would succeed at learning all the Boolean functions, for instance. So there were serious limits in their usability. And this was one of the reasons why research in neural networks was mostly abandoned until the 80s, when gradient descent and learning and backpropagation algorithm were developed. And this is what you'll see in the next video. Thank you. Bye.